Welcome again. I'm Zubair Akhtar, your instructor for microwave filter design course. So in previous classes, we have seen the filters, what are the different kind of microwave filters, and we have designed a couple of filters based on Butterworth design procedure and T. Procedure. So those filters are basically low pass filters. But in practice, we need to design certain other type of filters. They could be a band pass filter, band stop filter, and sometimes high pass filter as well. So the design procedure for designing high pass, band stop or band pass filter is quite depend on the lower pass filter, because we can translate the low pass filter to any kind of transfer function. It could be a band pass filter or it could be a high pass filter. In the previous class, the first class of the micro filters, like we have seen how high pass filter can be designed with the help of low pass filter. So we need to just transform the transfer function, say so that's to make a high pass filter. So mathematically we have seen like how we can convert the low pass filter to a high pass filter, and how we can design a band pass filter. So the thing is, like, just consider like we have a low pass filter like this and a high pass filter like this. If we club those responses to two transfer functions by considering the cutoff frequency for high pass filter is lower than the cutoff frequency of the low pass filter, so those two can create a band pass response. So let's see the transformation of low pass to high pass to a band pass or a band stop filter in more detail in this class. So I'll write down few common transfer functions, and we need to see like how they are defined in. So consider this is a very simple transfer function, this Hs. So S is the complex frequency. So let's, for the sake, just consider as a omega. So for lower frequencies, if S or omega is 0, the transfer function, say when S is 0, the transfer function for this is 1. Okay, when S is approaching infinity, so that means this gonna be whole term gonna be infinity, and 1 by infinity is 0. So transfer function reaches to a value 0. So for lower frequencies, its transfer function is 1. For higher frequencies, the transfer function is 0. So this transfer function is basically a low pass filter transfer function. Okay, let's see a very simple transformation on this. What if we make this transfer function and we define this S with 1 by S? So what gonna change in this transfer function? So this is going to change. So S divided by 1 plus S. Let's do the same analysis. Okay, so same analysis when S is approaching 0. So this is 0 upon 0. It comes out to be 0. So for lower frequencies, say S equals to 0, this transfer function gives us a 0. When we are making this S to approach infinity, what's gonna happen? So this gonna be infinity divided by 1 plus infinity. So this is not defined. So what we gonna do? We're gonna use L hospital rule. So with L hospital rule, we need to differentiate the upper part and lower part. So this comes out to be 1. So with L'Hospital rule, when we solve this limit, so the transfer function comes out to be for infinity is 1. So this basically for lower frequencies 0 and for higher frequencies it's approaching 1. If you are not aware of L'Hospital rule, so please go and visit L'Hospital rule for calculating the limits. Okay, so if this function gives you a 0 transfer function for lower frequencies and 1 for higher frequencies, so this is realizing a high pass filter. Okay, so what we have seen, if you have a low pass and if you want to convert a low pass filter to a high pass filter, you need to change S by 1 by S. Isn't that simple? Okay, let's see if we want to change the low pass filter to a say band pass filter. So what would be the transformation change? S, if we replace this S by S square plus omega naught square divided by S square sorry about this, yeah, BS. We'll define like what's omega square and what's B. So what we're going to change in our low pass response. Now we are replacing S with a new quantity. So S going to be replaced with S square plus omega square divided by BS plus 1. So this will result in BS divided by S square plus BS plus omega naught square. So again we need to put the values for very small frequency. For a very small frequency this is approaching 0, for very high frequency this is approaching 0. So in between it is at omega equals to S equals to omega square, it's approaching a higher value. So this is representing a band pass filter. So you can put the values of S and put the limits. Sometimes you have to use L'Hospital rule and you will see this transfer function is basically showing a band pass transfer function. So we know that band pass and band stop, they are slightly opposite to each other. So the similar transformation for the band stop, what we need to do? We need to translate with slightly opposite to the low pass filter. So what's it's gonna be? So it's, we need to replace the low pass transfer function with this. So it's gonna be BS plus omega naught square plus S square, and this factor gonna be up multiplied by S square plus omega square. So you need to see like how it is approaching. Okay, so for S equals to 0 it has some certain value, for S equals to infinity it also has certain value, and at S equals to omega naught it has some sort of null. So this is a band stop filter. So you can put those limits and you can find whether this transfer function is showing you a band stop characteristics or not. As a takeaway, so what we need to change when we are converting a low pass filter to a high pass filter. So for low pass to high pass, we just transform S to 1 by S. Okay. When low pass to band pass, we have translated S to BS S square plus omega square divided by Bs. So omega naught square is the center frequency and B is the bandwidth, so is the cutoff frequency 1 and 1, 2. Similarly, if we want to change a low pass filter to an equivalent band stop filter, so we need to change S with slightly opposite than band pass filter, just opposite to that. So it will give you a band stop characteristic. Okay? So this is the mathematical background of transforming the transfer function to the different kind of filter. So this is the basic theoretical background. So now we'll see one by one how we can change the low pass filter to high pass filter with some design examples. Okay, so if we discuss the low pass to high pass transformation in detail, so what we have seen, the S needs to be translated into the 1 by S. So what does it mean? You can also think of, say you have an reactive impedance which is j omega L and there is capacitive 1 over j omega C. So what this indicates, this transformation indicates omega needs to be replaced with 1 over omega. Should be like this. So if we change omega to be, say, omega dash 1 over omega, so this xl dash j 1 over omega into L and xc gonna come 1 over j 1 over omega into C. So if you see here this equation very carefully, the omega comes out to be in this form. So we need to change it to make it consistent. We can also write this as minus 1 over j omega 1 by L. We have multiplied by j, and so this, and for consistency, if we can write this as minus j omega into 1 by C. So what we have seen, if we have to use this transformation, so we have seen like the inductance is gonna be replaced with the equivalent capacitance of 1 over L value, and the capacitance would be translated into inductance with 1 over C value, and there is one negative sign also comes with this, so we can compensate this sign and we can modify our relationship for this transformation. So this, both the term would be positive. So now what we have to do this for transformation, all the inductance of low pass filter would change into a capacitance with value of 1 over L. All the capacitance of the low pass configuration, for high pass configuration, we need to change it to the equivalent inductance with a value of 1 over C. It's fairly clear. Okay, so how it gonna be like implemented, that we need to see in the next couple of examples. So as a whole, if we want to change the low pass filter to an equivalent high pass filter, so we need to replace the capacitance with inductance with the equivalent value of 1 over C, and similarly with the inductance. So let's have So you have low pass parameters like this. So I'm just taking a third order example for simplicity. So this is your G1, this is your G2, this is your G3. So consider this as our low pass filter design that you want to translate to a high pass filter, and let's consider its response at omega c is like that. Okay? And what we want? We want to make it the same filter as a high pass filter. So what we gonna change? We gonna change inductor to a capacitor, capacitor to a equivalent inductor like this. Okay? So how these values gonna be calculated? This G1 dash would be 1 over G1. This G2 for the high pass filter, it would be 1 over G2. And this G3, a capacitance well, G3 dash gonna be 1 over G3. And this will have a response somewhat like this. So this is high pass filter. So we have started with the one assumption with changing the omega replaced with some transformation, and we result in changing the equivalent C and L, and then suddenly we have seen like how we can translate a low pass filter to a high pass filter. Okay? So right now I have just explained in terms of G parameters. You can also relate these with the inductance and capacitance. It's really simple. So this is L1, this is C2, this is L3. Okay? So this gonna be, this capacitance, this gonna be 1 over L1. This C1 or C1 dash, this is gonna be 1 over L1. So this inductance, which is L2, which is equals to 1 over C2. And again here this capacitance, which is C3 dash, this gonna be 1 over L3. And we need to perform, these are like normalized with the source impedance and omega c. So we can translate it to any arbitrary frequency and any arbitrary load and source impedance with the similar procedure that we have followed in our low pass filter design. So this is a design philosophy of changing a low pass filter to an equivalent high pass filter. In the next class, we will see how we can translate a low pass filter to a band pass filter. So previously we have seen the transformation from low pass to high pass, and that is basically replacing omega with 1 divided by omega. Now in this class we are gonna see the transformation from low pass to band pass. So the mathematical transformation from low pass to band pass in terms of omega can also be written as like this. So this is omega square minus omega naught square, and this delta is defined, which is basically a fractional bandwidth, which is omega 2 minus omega 1 divided by omega naught. Okay? So all omegas, if we replace with this value, so this transformation results in a band pass characteristics, where omega 1 is the first cutoff frequency and omega 2 is the higher cutoff frequency, and omega naught is the center frequency. And these three are related as in geometrical mean configuration. For simplicity, we have chosen this. Okay, so this is the transformation. So let's see like how these frequencies gonna result in the transformation. Say for a low pass filter, our response would be like this, and there is a one frequency which is called omega naught here as a cutoff frequency. Okay. Now we need to translate this whole transfer function to another transfer function where this is equals to omega naught, and then we have a roll off like this, and we have a roll off like this. So this kind of transfer function along this omega naught, we want this transformation. So and consider this frequency as omega 1 and this frequency as omega 2. Okay. So see from this equation perspective what happens when omega is equals to omega naught. So this is equals to 1 over del omega upon omega naught. So omega naught upon omega minus omega naught upon omega naught. Okay, when omega equals to omega 0, this whole value is equals to 0. When omega equals to omega 1, say, we're gonna change here 1 over delta omega 1 divided by omega 0, omega 0 divided by omega 1, and this would be equals to minus 1. At omega equals to omega 2, 1 over del omega 2 upon omega naught over omega 2, this would be the normalized second point. Okay. Now we have to see like how the filters with this transformation be realized with the low pass filter. So for a low pass filter, we have this inductance, and this inductance is defined in terms of j omega Lk. This is a low pass prototype, right? Now what we're gonna do, we're gonna change this omega to newer omega for this value. So how it gonna change? J omega gonna replaced with 1 over del omega upon omega naught minus omega naught upon omega into Lk. So let's solve this. So this is j omega Lk divided by del omega naught minus j omega naught divided by omega into del into Lk. So if we see this very precisely, so omega is the variable here. So if we do a kind of j omega Lk divided by del of omega naught, and if we say plus 1 over j omega del over omega naught Lk. So this reactive element, while replacing with this transformation, it's giving me inductive reactance and a capacitive reactance with these two values, equivalent values. So we want to change a low pass filter to a high pass, so this should be somewhat like this, and this equivalent inductance would be Lk divided by del into omega naught, and the capacitance for this another element would be del upon omega naught Lk. So this is for like inductive element. What is going to change for we want to replace a capacitance? So suppose you have a capacitance in low pass filter and its reactance is defined as 1 over j omega Ck. Okay. Let's talk about in terms of admittance. That would be great. So this j Bk for a capacitance would be j omega Ck. Okay, now we replace this omega of low pass filter with the high pass filter configuration. What gonna change? Okay, so we'll put j omega as 1 over delta omega upon omega naught minus omega naught upon omega into Ck. So this is gonna be 1 j omega Ck divided by delta omega naught, and this is going to be minus j omega naught Ck divided by del of omega naught. Okay. So if we solve this again in terms of j omega, and this is Ck divided by del of omega naught, and if we say this is plus 1 over j omega, sorry, here we have omega, yeah, so omega and the equivalent value from this delta divided by omega naught Ck. So now we are talking in terms of admittance, and when admittance are adding to each other, that means we are talking of a parallel connection. So parallel connection of a inductor and a capacitor. Okay, so this capacitance gonna be replaced with the parallel connection of these two values. So this is the value of capacitor, is Ck divided by del of omega naught, while this is j omega L, and the L would be defined as 1 over omega naught Ck. So now if we want to change a low pass filter to a band pass filter, so we need to design first the low pass filter, we need to calculate all the values of low pass filter, and then we need to change those values to, like, every inductor gonna be replaced with a series inductor with a capacitor value, and these values for the new components, new inductance and capacitance, gonna be calculated with the original G values. So here Lk in terms of Lk, and there are few other parameters which are like del, and which is like basically the frequency parameter. And similarly, whenever we have a capacitor in low pass prototype, we need to change it with a parallel combination of inductor and a capacitor. So we have seen this transformation and how they are resulting in these equivalent values. So very simple. For example, if I wanted to demonstrate how these filters gonna be look like when we change this to say low pass filter to a band pass filter. So let's have a space here for a moment. So suppose you have a low pass filter, third order low pass filter like this. Okay. If you want to change to an equivalent band pass filter, so it's gonna be inductance, capacitance, then inductance, capacitance, and then you have inductance and capacitance. So this is the transformation we need to perform, and every inductor with this kind of a scaling we need to replace with inductor and capacitor, and every capacitor going to be replaced with a parallel combination of inductor and capacitor with these type of transformation. So with this method we can translate any low pass filter to an equivalent band pass filter. Thank you. In the next few class, like we'll do a complete example of designing a low pass filter, and we translate each and every component numerically to a band pass filter.